everyone. This is Chapter 8, Binomial Distributions. This is our third and final chapter for probability. So hopefully you have your notes packet in front of you and you're ready to take some notes. And let's get started. Alright, so here's an example of a type of problem we're going to be encountering in this chapter. In a manufacturing plant, the probability that a randomly selected part is defective is 15%. We're going to select a random sample of 8 parts. The question is, what's the probability that exactly 2 are defective? Now, answering this question is going to require us to think about the number of ways that this might happen. Okay, so for example, if we're selecting 8 parts and we want 2 to be defective, we could have number 1 be defective and number 2 be defective, but then the rest are okay. Right, that would be one way to do it. Or maybe the first 2 are okay, but then 1 and 2 are bad, and then the rest are okay. Or maybe we have the first one's bad and that one's good, and then bad, and then bad, and then bad, and then bad, and then the last one, and so on. Right, so there's lots of different ways that this could happen if we want 2 to be defective out of 8. Hopefully you remember from 9th grade Prop Stat that the way you calculate this is you would calculate this with a combination. A combination because the order doesn't matter. It doesn't matter what order they're in. We just want 2 to be defective. So if we're going to find a combination, it's going to be 8C2. That's the number of ways that we could get 2 defective. Then we have to deal with our probability. Well, if we want 2 defectives, that means 2 out of the 8 only occur 15% of the time. So it's 15% twice. If we have 15% happening, 2 of them are happening 15% of the time, the other 6 would be the good ones. They're going to be occurring 85% of the time because, and I pardon my writing, but I still have a broken thumb, is 15% happens twice, these are our 2 defectives, 85% happens 6 times, and that's our good ones. So we have 2 bad ones and 6 good ones, and this is the number of ways that we can arrange this. The 8C2 is the number of ways we can arrange it. So then if we multiply all that together on your calculator, that would give us our percentage, which winds up being 0.2376. So 23.8% probability that this occurs. Alright, so that's one type of problem we're going to be seeing in this chapter. The next type of problem that we're going to see is what is the probability that 2 or less are defective. So it extends the previous problem, and instead of simply having exactly 2, this time we want 2 or less. And we've done this type of problem before. So first we would have to calculate the probability that 2 are defective. Well, we found that earlier. We found that in the previous slide, and it was 0.2376. Then we'd have to find the probability that 1 is defective. So if we want 1 to be defective, that means it could be the first one, it could be the second one, it could be the third one, all the way up to 8. So there could be 8 different ways. So 8C1, we want 1 defective, which happens 15% of the time, which means the other 7 are all good. Well, the good ones happen 85% of the time. We want 7 of those. So we're going to multiply all that together, and we get a probability of 0.384. Now that's 2 ways and 1 way, but we also, it says 2 or less, so we also have to calculate 8C0, meaning no defectives, which means we don't want any defectives. Instead, we want all 8 of them to be good. So we'd have 85%, and we want that 8 times. And if we multiply that all out, we get 0.272. So to calculate 2 or less, we would add these 3 probabilities together for a total probability of 0.894. Right, so these are the types of problems that we're going to be doing in this chapter. Now I'm going to show you some shortcuts and some formulas that you need to know and you need to write down. So let's start off with what exactly we call this. This type of problem that we're dealing with is called a binomial probability, and it's up to you to determine when a particular problem or a particular example is binomial. So you have to know that a given setting is considered binomial if it satisfies these 4 requirements. First, each observation falls into one of just 2 mutually exclusive outcomes. It's either success or failure. It's either yes or no. So like in the previous example, it was either defective or not. So only 2 possibilities. Secondly, there are a fixed number of outcomes. It has to be a finite limit. So in the previous example, there were 8 in our sample, so 8 was the maximum. We can't just say keep going on forever. Thirdly, the observations have to be independent. Right? The defect versus the good, every single part was independent of the other one. Whether a part was good or bad was independent of each other. And the fourth one is the probability of success has to remain the same for all trials. Every single part had to have the same probability of defect, which was 15%. So you have to ask yourself, does it meet these 4 criteria? And if it does, then you can use a binomial setting and you can use the procedure that I'm going to show you. If it does not, then we have to do something different. And we haven't learned the something different yet, but we'll get there. Couple of notational things. If data are produced in a binomial setting, so it meets those 4 criteria that we just talked about, we call the random variable, x is the number of success, is called a binomial random variable. And we say that x has the binomial distribution, n is the number, and p is the probability. That is the notation that we use in statistics, so you want to make a note of that because that's what we want to refer it to. We've talked about normal distributions. A normal distribution is a continuous variable because a normal distribution would include all the decimals. It could happen 1.7 times, 1.6 times, 1.5 times. A binomial distribution is a discrete variable, meaning it's one part. In the previous example, it's either 1 part, 2 parts, 3 parts, 4 parts. So we can't find the probability of 1.5 parts being defective. Right? It's either 1 or it's 2 or it's 3 or it's 4. That's a discrete. Binomials are always discrete. So here's a couple of questions to go through real quick. Are these binomial distributions? If we toss a coin 10 times and count the number of heads, does it satisfy our 4 criteria? Yes, it does. Right? The top probability is the same every time, 50%. It's got a discrete number, 10, and they're independent of each other, and it's either heads or tails, so 2 things. So it meets all 4 criteria. What about if we deal 10 cards from a shuffled deck and we count the number of red cards? Okay, 10 cards, so it's finite. It's either red or black, so it's got 2 possibilities. But the probability doesn't remain constant. The probability of the first red card would be 26 out of 52. But the next red card would be 25 out of 51, and then 24 out of 50, and so on and so on. So the probability is not remaining constant, so therefore not a binomial distribution. 2 parents that have the genes for O and A blood types, and we want to count the number of children with blood type O. All right, so 2 possibilities, O and A. They are independent of each other, but it just says count the number of children. It doesn't say how many children, so therefore it doesn't have a fixed number. It doesn't have a stopping point, so therefore no, it's not a binomial distribution. Alright, so here's a probability distribution that we're going to use to do this. If we were to toss 3 coins and count the number of heads, find the discrete probability distribution. So one of the ways you could go about doing this would be to actually draw out your sample space. So you can make a sample space. Heads, heads, heads. Heads, heads, tails. Heads, tails, heads. Tails, heads, heads. Heads, tails, heads, and so on and so on and so on. If you were to do that, you would say, well, we could have 0 heads, 1 head, 2 heads, 3 heads, and the probabilities wind up being, there's 8 possibilities, so 0 heads would mean tails, tails, tails. There's only one way that happens out of 8, 1 out of 8, 0.125. 1 heads, that would be heads, heads, tails, heads, tails, heads, tails, heads, heads. So 3 out of 8. 2, and so on. So this is called a probability distribution. Out of 3 coins that are tossed, what's the probability of getting exactly 2 heads? Well, if you have the probability distribution in front of you, this is a really easy question. All you have to do is look up there and see. It's 0.375, 2 heads. We drew a sample space. Alright, so pretty easy if it's 3 coins. What if it were 12 coins? Right? Then you'd have a huge distribution, and that would be much harder. But if it works for 3, it'll work for 12, and I'll show you how this is going to work. Here's the formula you want to write down. If x has a binomial distribution with n observations and a probability p of success on each observation, the probability of exactly k successes in the n observations is given by this formula. Probability that the x value equals k successes equals n choose k, that's what the big parentheses are, n choose k, probability of k successes to the k power 1 minus the probability to the rest of them. N choose k with the parentheses is just yet another symbol for combination. In ProbStat in 9th grade we use the C, NCK. The further you get in math and the more higher level mathematics books, they start using N choose k with the parentheses instead. Alright, so in this to tackle our problem we just did using this formation, this formula. Out of 3 coins that are tossed, what's the probability of getting exactly 2 heads? So the probability that x equals 2, 2 heads, would equal 3 choose 2, there's 3 coins, we're choosing 2 of them, times the probability of a head is 50%, so 0.5 to the 2, times the probability of a tail would also be 50%, and we want one of those. Multiply all that together, 0.375. Exact same answer we got when we were able to write it all out. This formula is very handy because you're not going to be dealing with something as simple as 3 coins. You might be dealing with something like 12 coins, in which case writing out the distribution is just not feasible. Okay, another example. The number of inaccurate gauges in a group of 4 is a binomial random variable. The probability of a defect is 0.1, so 10%. What's the probability that only 1 is defective? Using our formula, this is what we would write. Probability that x equals 1 equals 4 inaccurate gauges, we're choosing 1, so 4 choose 1, times 0.1 to the first power, because the probability of a defect is 10%, times 0.9 to the third power, because if it's defective 0.1 times 10%, then it's good 90%. Multiply all that together, 0.2916. Right, pretty easy. What about more than 1 defective? More than 1 defective would be the probability that x is greater than 1. So that would be the probability of 0, would be the probability of 2, 3, and 4. So we could go about this by calculating the probability of 2, the probability of 3, and the probability of 4 and adding them all together. Or we could do 1 minus the probability of 0 plus the probability of 1. We already found the probability of 1, so if we just calculate the probability of 0, add that to the probability of 1, and then do 1 minus that all, we'd wind up getting the probability that is greater than 1. It's a little bit easier than doing probability of 2, probability of 3, probability of 4, and add them all up. How you do this on a calculator. Nice little feature on our calculator. So this is for the TI-84. It also works for the Inspire. In your calculator, there is a button on the 84, the distribution button. It's right underneath the arrows, DISTR, and if you hit turn that on, so second distribution, and then you go down, all the way down to letter A and letter B, there's 2 commands. The first one is binomial PDF, and it requires you to type in 3 things. N is the number of trials, P is the probability of success, and X is the number that you want. Okay, so X equals K, the number of successes. Now, binomial PDF gives you the probability of a single binomial. So, probability of exactly 2 or exactly 4. Binomial CDF, which is directly underneath the PDF command, calculates the cumulative probabilities. So in other words, if we want to know the probability of 2 or less, that would be the probability of 0, the probability of 1, the probability of 2, we could use this feature to let us calculate that. So it's a very handy feature when you're dealing with really large sets. And let me show you how we're going to use these. Alright, so here's another example. A genetic trait of one family manifests itself in 25% of the offspring. If 8 offspring are randomly selected, find the probability that the trait will appear in exactly 3 of them. So we're going to use our calculator this time. Probability of x equals 3, and this is important. I want you to write that notation. Probability of x equals 3. I'm going to require it on my tests and quizzes, and the AP exam requires it on theirs as well. So get in the habit of writing this notation. The probability of x equals 3 equals binomial PDF, because we're trying to find exactly 3 of them. There's 8 offspring, so 8, comma, number of probability is 25%, comma, we want 3. Hit enter, boom, there's your answer, 0.2076. Okay, an extension, at least 5. Well, at least 5 means 5 or less, 0, 1, 2, 3, 4, 5. So this one then would be a CDF problem. At least 5, sorry I said that wrong. Probability of at least 5 would be 5 or more. All right, you got to be careful on these, it's very easy to get confused. At least 5 means 5 or more, so that means 5, 6, 7, and 8. So we want to find the probability that x is greater than or equal to 5. So we're going to do 1 minus the probability that it's less than 4 or less. So we would use our calculator to do binomial CDF up to 4, so that calculates 0, 1, 2, 3, and 4, and it adds them all together, and do 1 minus that. And then there's your answer, 0.0273. Okay, we'll do one more example. In a certain county, 30% of the voters are Republicans. 10 voters are selected at random. Find the probability that no more than 6 of them will be Republicans. No more than 6. So you have to think about, what does that mean? How are we going to do that? All right, here's how it works out. Probability no more than 6. So 6 or less. That's a CDF problem. So 10 Republicans, 30% chance. We want 6 or less. It's a CDF. Punch all that in, you get 0.9894. What is the probability that at least 7 are not Republicans? At least 7 are not Republicans. Alright, that would be 7 or more. So probability x is greater than 7 would be 1 minus the probability, the binomial probability, 10. Now notice the other change, not Republicans would be 70%. So we would do 70% not Republicans, 6 or less, and we get our answer. Alright, for homework tonight, I want you to do the next page in your packet. And the next page of your packet has 4 or 5, maybe 6 problems that I want you to do exactly like this. So do the back of this note page, do these problems. When you get to geometric probabilities, distributions, stop. Alright, very good, and I will see you in class tomorrow.